Hi there, Hire. Today we're going to be looking at diffraction. We're going to move on from interference last week and talk about diffraction. Now, hopefully you'll be in school at some point this week, so we'll be able to go over this with you a bit more in class if you need to, and also go over anything else from previous weeks as well if you need a wee bit of support and a wee bit of help. We're still setting the task this week that we expect you to work on when you're in school, and also if you get any time at home, and we'll need to take that and just see how that works out over the next few weeks. Okay, so first of all, what is diffraction? So diffraction is one of the wave properties that including reflection, refraction and interference. So if something diffracts, interferes, reflects or refracts, then it is a wave and it has wave properties. There's also, remember, wave particle duality, where particles can also behave like waves, and if a particle diffracts, then it has wave particle duality properties such as an electron. Now, diffraction is the bending of waves around objects. Now, Mr. Huggins doesn't like the word bending, but it's because if you look at this diagram on the bottom here, you've got this the change of direction of the wave as it hits an object. So if it hits an object like this, it will curve, if you like, or bend, or it will change direction around the edge of the object like that there. If it hits a gap, it changes direction or it bends around one edge of the object and also the other edge of the object. And the size of the gap determines the amount of diffraction that occurs, and also the wavelength determines the amount of diffraction that occurs. So the longer the wavelength, the more it diffracts, the more it bends. And if the smaller wavelength, the less it diffracts. And here is a little diagram just showing you what it's doing there. Here is a wavelength, a waveform coming in, and you can just make out there that it's kind of bending around, it's diffracting around the edges like that, and it's producing this kind of curved path in front of the gap there. So, yeah, last week we talked about something known as coherent waves. Now, coherent waves have a constant phase relationship, and they will also have the same wavelength, frequency, and wave speed. Now, diffraction can create coherent waves for us from a single source. Now, that's really useful because we don't have to mess about with two sources, say two speakers or two light bulbs. Then we can create we've got one source and use diffraction to create our two coherent sources. So diffraction can be used to create two or more coherent waves from a single source. By using a single source and splitting it into two sources, this guarantees the waves are coherent. The problem with if you've got two sources is you can't guarantee that that's a coherent wave, because there could be a variation slightly in the speaker or a variation in the light bulb, and you're not necessarily getting a coherent wave. Whereas if you start with an original source and put it through a diffraction gap, two gaps, then you can create two sources, and those sources will be exactly the same as the original, and these two sources will be coherent. This is what it looks like here. There's two gaps. Here is a single source coming in, and we use these two gaps to create two coherent sources. What's happening in the bottom diagram here is known as Young's double slits experiment, and this is used very often to create interference patterns. And you can see here the wave coming in. You've got two coherent sources produced just like it is here, but if you look carefully, you can see there you've actually got a zero order maximum down the middle, because that's right in the middle of the white. This is its side on, so it's nice bright white and light in the middle. You've got a zero order minimum here, because that's going to be it's going to be destructive interference, and then you've got a first order maxima, first order minima, etc. on either side. That is what it would look like for the interference pattern, and this is what it looked like if you looked at it side on. We're going to look at a wee more detail at that, and some of the questions you've been doing in the booklet might be more familiar to you now we explain this. Right, so diffraction isn't just about that double slit. Diffraction also has something known as a diffraction grating. So a diffraction grating is more than just a double slit. So in the previous slide we talked about just two slits creating two sources. If you have a piece of perspex perspex glass or plastic, and you put lots and lots and lots of slits in it, then you can create multiple coherent sources, and that strengthens up the interference pattern and makes it a lot clearer. And that's called a diffraction grating. You etch the lines, so if you etch the lines on the perspex glass or plastic, they act as barriers because the light can't get through. So if you take a piece of glass and you scratch it, then you see that scratch, the light doesn't come through. If you scratch all over the glass, you won't be able to see through the glass. So the scratch acts as the barrier, and the spaces between the scratches act as the gaps for the diffraction grating to cause interference or multiple coherent sources. This results in thousands of coherent sources and a strong interference pattern produced. The spacing between the etched lines affects the spacing between the maxima lines produced. So the closer together the lines are in the diffraction grating, the further apart the maximas in an interference pattern, the further apart these lines would be. These are the maxima lines, second order, first order, second order. So there's a diffraction grating there. The closer together the diffraction grating spacing, the smaller the D value we're going to call it, the further apart the maximas appear, and the greater the theta becomes, which is the angle between the zero order maxima and the order of maxima that you're looking at. We're going to talk about that in a second. So diffraction grating spacing, is symbol D, is often confused with lines per millimetre. This is on purpose. Questions try and confuse you so that it gives you a little bit more calculation to do. It's not lines per millimetre that we want, it's the actual spacing between the lines in metres. So we have to convert between the two. And at the side here is I've tried to explain that to you. So the diffraction grating spacing, not spacing, spading, I should say spacing, I'll fix that in another slide. The space between the lines in metres. D is not the number of lines per millimetre, but you might be given it that. So if you're given 100 lines per millimetre, that's going to be 100,000 lines per metre. So if there's 100 lines per millimetre, there's going to be 100,000, because 1,000 millimetres in a metre, there's going to be 100,000 lines in a metre. And what is the spacing between these lines? Well, 1 metre divided by the 100,000 gives you the actual spacing between them in metres, which would be 1 times 10 to the negative 5 metres. So you'll see this here. Times it by 1,000 and do 1 over it, and that will give you the actual spacing. I'll show you what that looks like in the past paper question that we're doing at the end of the slides today. Right, there is an experiment, very common experiment for diffraction grating that we use. That has, very similar to the last slide, a source of monochromatic light. Monochromatic means single colour, and that's to stop any multiple amounts of diffraction or spectra produced. So that'll be a laser of some description. Diffraction grating here, you've got a zero order maximum in the middle, bright band of light, and you would have another bright band, whatever angle up. Now, there's going to be multiple bright bands of light because there's going to be multiple maxima. And the first thing you probably need to do is choose between which two bright bands are you measuring this angle theta between. So say the angle to the first order maxima, or the angle to the third order maxima, or the angle to the first order maxima, and that would be your angle of theta. So a diffraction grating can be used to calculate the wavelength of a light source. If the wavelength is known, this can be used to calculate the diffraction grating spacing. In every case, it's usually the angle that we're trying to work out, and then that gives us, or we're given that, and when we have to then work out wavelength or diffraction grating spacing. The experiment is shown in as set up as shown in the diagram. A single wavelength colour light is used. This is referred to as monochromatic. And we use this formula here, you find that in your formula sheet. M lambda equals d sine theta. M is the order of maxima you're choosing, so if it's between the zero order and the first order, then that would be 1. If it's zero order and second order, M would be 2. Zero order and third order, that would be 3. But it's also always the zero order maxima in the middle to whatever maxima you're picking. So M would be the order of maxima that you're picking, that you're measuring the angle up to. Lambda is the wavelength of the light, or the monochromatic light source used, single wavelength. If you use white light, it wouldn't have a single wavelength. It'd have a multiple number of wavelengths, so we can't use the formula for that. D is the diffraction grating spacing, just like I showed you in the last slide, and theta is the angle, and we do sine of the theta, and that's how we work it out. You can just substitute and rearrange for the one that you want. Sometimes the angle is not given, but we are given the distances between the grating and the screen. That would be, in this example here, B, and also the distance between the zero order maximum and whatever order of maxima that we're interested in, and we do an inverse tan of that. It's just a right angle triangle, it's just trigonometry. The tan theta equals opposite over adjacent, and we can rearrange that to say theta is tan inverse of opposite over adjacent, or tan inverse of A over B. So we can do that there to get theta value, and then use that theta value in the formula to calculate wavelength, or if we've got wavelength, diffraction grating spacing. quite straightforward, very common question to be asked in an exam or an assessment. Okay, now we need to know a little bit more about colour and diffraction gradient. So what if we don't use a single colour light source, a monochromatic light source such as a laser? What happens? Well, we know that from refraction, which is this one here, that if you put white light in, we can turn it into a spectra. We can turn that white light into all its component parts from red all the way through to violet. We can do something similar with diffraction as well. So this is refraction working, this is diffraction working. We use a diffraction grating with white light. Now, a very important point is that the zero order maximum doesn't turn into a spectra. And the reason being is because the central maximum is caused by zero path difference. There is no path difference in the zero order maximum. There is no phase difference. They're not meeting out of phase. Every colour of light is meeting at the same time. In the middle there, there's not this interference, there's not this difference in wavelength that's caused in the middle. So you always get a white light right in the middle. Because the central maximum is white light caused by zero path difference and all the wavelengths of light meeting in phase. So the white light in the middle is caused by the all meeting in phase, and in fact there's zero path difference. As you move away from the central order maximum, this whole block here would be your first order maximum. And it's a large spectra that you get. Red is going to be diffracted more, so it appears at the outside edge. Violet or blue is going to be diffracted least, so it's the inside edge. And sometimes they ask you to explain why that's the case. And we can use our m lambda equals d sine theta formula to help explain that. So red light is diffracted more than blue due to its longer wavelength. And due to the m lambda equals d sine theta, the formula we had in the last slide, we know that the wavelength of red is greater than the wavelength of blue. That's this side of the equation. So therefore, if the wavelength of red is greater, then d sine theta must be greater. D is a constant, so sine theta must be greater, therefore theta must be greater. So the angle between the zero order and the red must be greater than the angle between the zero order and the blue or violet. So diffraction and refraction can be used to split white light into its component parts. Shorter wavelength light refracts more, blue, violet light will refract more than red. Longer wavelengths diffract more, red light will diffract more than blue, violet, red. Now, these are the wavelengths, the general wavelengths of light. You don't need to remember them specifically, but it's important that you know ballpark figure what the wavelengths are. So blue light is around about 480 nanometers, green light is around about 500 nanometers, 509 nanometers, and red light is around about 650 nanometers. So if you think about 450, 480, 500, 640, something around about that, it'll give you an idea. You don't need to know the specific number. If you need to use the number in the calculation, then normally you'll be given it. You don't need to know specifically a number, but it's good to know roughly what these numbers are. If you are given a wavelength of light, you should be familiar with roughly what colour it is. So if you're given 640 nanometers, you should be able to say, well, that's kind of red. Or 650 will be kind of red. If it's going to be 500 nanometers, you should know it's green. So you need to know roughly what the colours are for the wavelength. Okay, that takes us on. That finishes off theory in that. I'm just going to look quickly at a past paper question. This is from 2008, question 8. And you're given this diagram in this question here. A student investigates interference of light by directing laser light of wavelength 630 nanometers onto a grating as shown. So you've got the laser, monochromatic, 630 nanometers, you've got a grating, you've got the zero order maximum here, and then you've got what would be the first, second, third order maximum here, and you're given the angle between them. It says there a pattern of bright spots is observed on the screen. Explain in terms of waves how bright spots are produced on the screen. Okay, so it's asking why do you have these bright spots? These bright spots are caused by the constructive interference. So what is constructive interference? It's not okay just to say it's constructive interference. You need to explain. So if it says state what causes it, you could maybe get away with saying constructive interference, but you have to explain what causes it. And to say constructive interference, that's not an explanation. So what is constructive interference? It's worth 1 mark. Waves meet in phase. Crests meet crests, troughs meet troughs, or that the path difference equals m lambda. All those are the explanation of constructive interference. You can accept the word peak instead of crest like I was doing the other week there. You can show by a diagram. You must be showing how you get constructive interference, and we don't accept the words join or merge. Then it says a grating is 250 lines per millimetre. Alarm bells ringing. 250 lines per millimetre needs converted. Calculate the angle theta between the central maximum and the third order maximum, and you have to do 3 marks for that. So m lambda is d sine theta, 1 mark. Plug the numbers in. You're not getting an extra mark for doing your diffraction grating spacing, unfortunately. So it's just 1 over, it's 250 lines per millimetre, so it's 1 over 250,000 times sine theta, rearrange for theta, you get 28 degrees, 3 marks for that. You're allowed a wee bit of tolerance with that, and you don't get any extra marks just for the substitution. And for this one here, what they've done, they've put in just a slightly different way of doing the d value, but I think it's 1 over 250,000 is much easier to understand. Question part 3, the grating is now replaced by one which is 600 lines per millimetre. So that is 6, what's this one here? This one is 250 lines. It's now 600 lines. So there is more lines per millimetre, meaning that the spacing between the lines is smaller. And I've already said to you, if the spacing is smaller, then the angle is going to be greater and the spots will be further apart. So the grating is now replaced by one which is 600 lines per millimetre. Greater lines per millimetre, smaller actual spacing. State the effect of this change on the pattern observed. Okay, so the spots will be greater. They've mentioned spots here. So the spots will be further apart. You need to know that. And explain, state the effect and justify your answer. So the spots will be further apart, or the angle theta will be greater. That would be a greater angle. Those two will get you the 1 mark. Why is that? Because the slit separation d of the new grating is smaller than the previous grating. It gave you lines per millimetre, didn't mention the slit separation, so the slit separation is going to be smaller. You can do a calculation, however you don't have to, and there's the solution there, or what it's asking you there. So the interference pattern is produced by coherent light. State what's meant by the term coherent. We did this last week. Constant phase relationship. Now here it says the waves in the laser have, you don't have to say that, constant phase relationship. And they have the same frequency, wavelength and velocity. The bits in brackets are not needed. The bit isn't needed is constant phase relationship. I spoke to you about that last week, really important, that's your 1 mark. And in phase is not sufficient. That when you say coherent, it has to be constant phase relationship. So there are some questions out your question booklet I'm going to give you to do this. And there is also a past paper homework which on interference that will be given out for you to work on as well next week. I'll get all that out to you on Monday, or this will be the Monday for you, a wee bit later, and you can continue working on this when you come into school, and hopefully we'll see you all next week, and you're good to get back into school and get back into your physics. Okay, any questions, concerns, as you know, speak to us when we're in school next week, and you could also email me and I'm happy to help anybody that I can.